I want to talk to you about material dilution. You know, we do dilute solid materials, not just fluids. This sponge here consists of 50 parts of space and 1 part of plastic to give us a solid lump of foam plastic. So we've really diluted the plastic 50 times. And we finish up with a different material. It's a material which is nice and soft. Now, I call a material like this, I call it a macro material because of the macroscopic properties of the cells within here. Now, engineers do this all the time. They're always adding space to their structures. This tube has got a lot of space in the middle here. And why do we want that space? It's to increase this lever arm so that we have got a strong member when we try and bend it. There's a big lever arm here, so since the strength in bending is proportional to the strength of the material there and its lever arm, the more lever arm we can get without using any more material, we're just getting free strength. And that's what engineers are doing all the time. They're designing their shapes very, very carefully in order to get the maximum benefit from their lever arms. So we've got this solid rod here which we can bend very easily, and we can compress and make it buckle. And once it buckles, it's lost all its potential for getting stronger. It's failed in effect when it's buckled. And engineers have to be very careful not to have members that buckle while they're in service. And by adding a bit of space, we can get a much bigger lever arm. You know, this member has just the same amount of material as this one, but it's much stronger in bending. So what does shape do to material? It transforms it. It transforms plastic into foam plastic. Now, does an engineering repeating shape like this lattice, does this also transform the plastic of which it's made into a macro material? Well, of course it does, but it's not commonly recognized, because what shape would you use for the macro material to make them equivalent? Well, the answer is you use this shape here. And it's a very different shape. It's bigger than what it's trying to represent. And the rule for deciding what square cross-section we should have here is that this new shape should have the same radii of gyration as the shape it's going to represent. And this determines straight away what shape this cross-section has. This one is square because this is square, but if this were a rectangular section, this also would have a rectangular section, and it would be the 2 radii of gyration which would determine its shape. Now, engineers will know what I mean by radius of gyration. Now, once we've determined this shape here, we can work out the properties of the macro material in it. First of all, this is very light. It's just the same weight as this. And so, of course, its density is very tiny, because we work out the density of this by taking the mass per unit length of this member and divide it by the cross-sectional area of this one. Likewise, the stiffness is got by working out the force per unit strain of this member and dividing that by this area here to get the Young's modulus of this material. And the strength of this macro material is going to be the force which makes this break in compression, and it will break by buckling these chord elements. They will buckle into a sinusoidal shape, and that's the maximum load you'll get out of this member. And that's a force, ultimate force. And we take that ultimate force, divide it by this cross-sectional area, and we get the ultimate stress in compression, the ultimate compressive strength of this macro material. And that is very, very useful because it's quite tricky to work out the buckling strength of this, but it will always be the same for this particular form. So once we've worked it out, we are armed with a macro material to design with a known strength. And our dilution factor is not based on the actual volume of material to the ratio of the volume of the space, if you like, to the volume material. It's based on stiffness, because stiffness is the most important property of a material, and the dilution factor is defined as the Young's modulus of this material here, its stiffness, divided by the Young's modulus of this material, which of course is very small, and the dilution factor for this shape is 120, much more than the 50 of the sponge. And this has a buckling strain of 5.7 millistrain, quite a decent engineering ultimate strain. Now, how are these ideas useful? Well, engineers are designing shape so much. It's what preoccupies them. And the possibility they have now with the idea of material dilution and a whole palette of different macro materials to design from is that they start with a very simple envelope shape of their structure. They need to know where all their forces are, and they need to know too what the stiffness criteria are. Not easy. Strength is easier to cope with than stiffness. And they also need to know things like what's the minimum thickness of material that they're prepared to entertain. And once they have set those parameters, they've got an amazing choice of macro materials to fill that space. Maybe there'll be very concentrated material at certain points where the loads are applied, a bit like with this. There's less dilution at the ends here than there is in the middle. So there's going to be all that to cope with. But engineers should be greatly helped by having a much broader concept of what they're trying to do in design. So I finish with going back to my strut. This solid strut buckles like this, and this beautifully structured strut is 13 times stronger without using any more material, but using a lot more space and a lot more of an intricate shape. And that, of course, is what designers are grappling with all the time. Now, I hope you've enjoyed this video. There's much more information on material dilution and macro materials on my website, which is dilution.xyz. And I hope you have enjoyed listening to this, and I hope that you might be helped in your engineering design by having listened to it. Thank you.